Hi, welcome to some interesting bit of content for the Libra Hub channel. I'm Tobias Wenzel, professor at the Pontificia Universidad Católica de Chile, and today we bring you a really interesting bit of content through our partners Bioimaging North America, specifically the Builders Group, where we get together with other professors around the world to talk about how to build and share open microscope designs. And today we will hear from Spencer LaVere Smith from a startup or from a small company called Optica. And that's a really interesting bit of content because they have brought something really new to the market. So usually microscope design is about how to arrange relatively standard portfolio of optomechanics and optical components. However, they have innovated the lenses and the geometry of the lenses themselves, and they are the only provider of some pretty spectacular large field of view light sheet microscopy optics, and they have actually made the actual lens assembly, the objective themselves, open source. So let's welcome him and hear from their experience.
So Spencer is a professor at UC Santa Barbara, where his lab works on neuroscience, optics, and computation. He's also the CEO of Optica, which specializes in laser scanning multiphoton imaging. So he's well known for advancing large field of view multiphoton imaging in the community, including open source custom optics. And he also runs LabRigger, which a lot of us are very familiar with. So Spencer, over to you.
Thanks so much. Thanks for having me here, Gil. And I echo a lot of the things that John said. I've got a similar Venn diagram at the end that he started with as well. So I think we think similarly about these issues. So yeah, Pacific Optica is the company that we spun out from the lab. I want to talk a little bit about the evolution of microscopy optics and kind of where we are today. So originally, like around the time of Galileo, the first microscopes that people made were completely bespoke. And we still have bespoke microscope builders today, and that's great, but these were really bespoke. Like every single lens was unique to that particular microscope. And those were beautiful pieces of work, but around like 1858, the Royal Microscopical Society decided they needed to lay down some standards so that you could have some interchangeable parts. This is right around the beginning of the Industrial Revolution, and there was a recognition that this would be a good thing to do. And it was. So objective threads were standardized, slide sizes were standardized, and other things, and we still have those standards today. These are the same standards that kind of govern why all of our objectives are basically the same size. So when home builders go and want to build something, for a lot of these low NA components, where you may be relaying an imaging plane or something like that, if you're working below NA of about like 0.4, you've got a lot of options. But once you start getting into higher numerical apertures, there's really only 4 companies in the world. There's 2 in Japan and 2 in Germany that sell these optics. And that's the way it's been for a long time. And there's this architectural lock-in that's happened. And this is it's not just in microscope optics, it happens in all sorts of fields. But basically, it's a specific set of design choices is so foundational that changing them would require re-engineering the entire ecosystem. And so this is an architecture that, when we grab parts off the shelf to build these really innovative imaging systems that we've been talking about, these custom bespoke systems, the bottleneck is always the high NA optics. We've got to grab something off the shelf. And this is an architecture that hasn't really fundamentally shifted in 170 years. So, this has really led to a stagnation. Microscope users put it up with it because they have no choice. The stagnation really slows progress in biomedical research and clinical imaging and advanced manufacturing and more. So we have these small fields of view where we have really nice performance right in the middle of the field of view, but it vignettes really rapidly. And most manufacturers, actually, I don't think any of them, will actually show you how fast it drops off towards the edge of the field of view. It's not until you start imaging beads at the edge of the field of view that you even realize that. It's slow imaging, short working distances. And this is very frustrating for me. I recognized this issue when I was a postdoc, and when I started my lab, I started building optics so that we could do something better. So that effort has evolved into the diesel 2P system, which gives us this really big field of view for multiphoton imaging. It has two completely independent beams going into it. I'll talk a bit more about that here in a little bit. The Ventana scan engine, which I'll talk about a little bit as well, which has really solved an engineering trade-off in beam scanning. We found a trick where we can have a non-inertial mechanism for multiplying the beam scan angle. And then we had another problem where we needed to have a really long working distance for two-photon applications. And most of the objectives that people were using had fairly short working distances and required water immersion, and it was really incompatible with a lot of the types of experiments that people wanted to do. And so we kind of broke some of these rules about what objectives need to look like and the size envelope that they need to fit in. And we're able to create something that was a bit of a hit in ways that I didn't expect. So the key thing that we do is we build the whole system independent of these legacy companies. We don't use anything from Nikon or Zeiss or the big major manufacturers. We've developed a fabless approach for innovative optics, and so we're flexible and can quickly adopt new technology. And we have manufacturing partners in the US and abroad, and honestly, that's like the vast majority of my time at the company is working with these manufacturers to make sure that they can make the things we want. And since we know the optics, we know the user applications, originally I was just open sourcing all this stuff, but it turns out that people, very few labs have the expertise to actually do precision alignment of custom lenses in their lab to build a custom objective. And so I worked as a consultant for a little while to coordinate manufacturing runs. We just realized that there's actually a lot to do, and there's a lot of potential impact we could have. And we've been really pleased at the results so far. So the Diesel 2P has sold into numerous labs across 6 different countries in less than 2 years after publication. The CUSA is sold into 40 labs around the world in less than, I think it's more than that now, less than 2 years after the publication. And this Ventana system I can tell you about has sold into the most demanding labs literally weeks after we even introduced it. So we're happy with the impact that we're having so far. So we can talk a little bit about the Diesel 2P if you're not familiar with it. Basically, it's one of these mesoscopes. So you've got submicron resolution X and Y. Has a field of view of about 25 square millimeters. We actually went out to a span of 7 millimeters with adaptive optics at the edge to kind of squeeze out a bit more field of view. And what's unique about it is it has 2 completely independent pathways going to the objective. So they're not yoked to each other at all. So you can set the system up in a lot of different ways. And they're combined with polarization, not wavelengths. So you can have the same wavelength in both arms. And do temporal multiplexing. You can look at, a big field of view and a small field of view, or 4 different fields of view, kind of switching between them rapidly, interleaving them. Or you can do random access in one and large field of view in another. And it can be anywhere in that large 25 square millimeters of tissue. I wanted to do this so I could see multiple brain areas at the same time, particularly primary visual cortex and higher visual areas in a mouse. We also want to do some ontogenetics. You can run both wavelengths through the same pathway, but just to kind of, the simpler implementation of this is to run 910 nanometers through one arm and 1040 through the other. And so you can have random access in one and a large field in the other. And we've done things with like using an SLM to make multiple dots and spiral scanning them, and we can reliably activate cells. And we have a whole series of experiments that we were doing with that. The CUSA objective was trying to solve this problem where conventional short working distance water immersion objectives that are typically used for multiphoton imaging in vivo, they can give you nice imaging if everything's right, but you can fall out of that optimum very easily. And sometimes there's even just mechanical issues where you can't get the objective up to the close enough to the plane of focus that you want. And we went back and forth a lot trying to figure out what geometry would work until finally I threw up my hands and said, let's just get a cone of light in and out of there. Let's move the entire optics 2 centimeters away, 20 millimeters away from what we want to image. And then we made it really wide, right? We have to, because we've got a cone of light coming in and out. But this solved the problem. We also made it air immersion. One of the first things I realized in some of our experiments with custom optics for multiphoton was that air immersion worked. I thought that the spherical aberrations and these other issues would be crippling, but it turns out that it's actually fine. It works really well. And the ergonomic benefits are massive. So if you've got some experiment that's running for many hours, a water interface can shift over time, and you have to get back into the system and realign it. And with air immersion, you just don't have to deal with that at all. It's great. And what I didn't realize is that people who image through Gren lenses and prisms and periscopes and other types of imaging, they also find this useful. You can get neuropixels probes in there. There's lots of applications for having this really long working distance. Here's some specs of it. So it's really optimized for multiphoton, really high performance. It's we also optimize for fairly large scanning angles. So we tried to make it compatible as we could with conventional microscopes. So that people who use this on Bruker or Zeiss and Olympus and LaVere and other types of imaging systems. But we recognize very quickly that we want to push beyond these scanning angles. So most systems cannot do that full, excuse me, plus or minus 3 degrees scanning angle. And so we have a new version of this, the avocado I'll talk about here. So for most systems, there'll be a 2 millimeter by 2 millimeter field of view. And if you can go out to plus or minus 5 degrees, you can get a 3 millimeter by 3 millimeter field of view. And we do that with the diesel system or with our Ventana systems. But the CUSA, just on regular microscopes, you can, working in adult ferrets, which have these really thick skulls, that optical window has a lot of biology up and around it, anatomy around it. And it's hard to get objectives down to the cells that they want to image. And other options like the Edmund Optics 20x.6 isn't optimized for multiphoton. And so the CUSA was really enabling for those particular experiments. It also works well in younger ferrets, tree shrew. Somebody wanted to use it for intact imaging in pig retina, which is a common preclinical tool. This is apparently the first imaging of cochlea in vivo. It has this really complex surgical preparation. We're coming in from the ventral aspect, and other long working distance air objectives that they had, like this Nikon 20x.4, wasn't optimized enough for multiphoton and was burning cells. So with the CUSA, they could use much lower power, be much more gentle with the cells. And this is apparently the first functional imaging of hair cell activity in vivo in mice. It also worked for 3-photon, which we didn't design it for. But typical 3-photon microscopes use really high NA objectives, which they don't need to do. You can actually use, this is through 20 millimeters of air with a 0.5 NA objective, and we're able to get really nice images. So this is focusing down through mouse neocortex, third harmonic generations in cyan, and Texas red is the blood vessels. So iterating on this, we did the avocado, which is a little bit higher NA. It's also a little bit higher magnification as well. So the field of view should be smaller, but we optimized for large angle scanning so much that the field of view ends up being basically the same. So you can get about a 3 millimeter by 3 millimeter field of view if you're scanning at these high angles. So our point spread functions are smaller. It's basically the same in X and Y, but the axial, you can see a little more of the difference in the axial full width at half max. We get really nice signals. It's diffraction limited over plus or minus 4 degrees scanning, and plus or minus 5 degrees scanning is usable. And then we went to the scan engine. So those are the CUSA was for the objectives, and now we're working on the scan engine. So that we have these optics for the scan. The first thing we needed to do was we needed different scan lens and tube lens optics. So these are, if you're familiar with the threading of Thorlab's components, this is an SM3 threading on that tube lens. So it's a big tube lens. And the Ventana SL, that's a SM2 threading on that bottom aspect. So these are larger, right? If you wanted to higher throughput, higher space bandwidth product, you need to go to larger optics. What we're trying to address is this fact that scan mirrors are inertia limited. So as you go faster, the mirror size gets smaller. And as the mirror size gets smaller, that means you need to magnify the beam more. As you magnify the beam more so that you can overfill your objective, you end up minifying the scan angles by the same factor. So there's this trade-off, and we wanted to avoid that trade-off. And we found a way to double and even just arbitrarily angle multiply or angle amplify by even higher factors. So even with the same optics, you can go much faster. So this is what it looks like inside. So we've got this angle doubling unit, which is basically a relay to another Galvo scanner, sending that back through a polarizing beam splitter, then to the objective. And we need to do, there's a lot of different ways to mess this up. The scan lenses have to be perfect and the tube lens needs to be perfect. But we found ways to do this in a diffraction limited manner. And so this is the Ventana Fast system. These are now turnkey that we sell at the labs. We can do 1 millimeter by 1 millimeter at 4 frames per second with a lot of photons from each individual cell. The Ventana Wide is even larger, so we can go to 3. These are 3 by 3 millimeters. We can actually go up to 3.2 by 3.2 millimeters. And what was really key to get this to work was these, again, custom optics. So the tube lens and scan lens just provide diffraction limited imaging over much larger scan angles. The color lookup table on here is Strel ratio. So what this lets us do is scan a lot of lines very, very quickly. So the Thor Labs mesoscope is a beautiful system. It does 12 kilohertz scanning, so 24,000 lines per second. But the scan lines are only about 600 microns wide. So they do 14,400 millimeters scan per second. The Diesel 2P does 24,000 because the resonant axis is 1.5 millimeters. And since there's two beams, it also goes up to 48,000 millimeters, but we'll just talk about a single beam just to make fair comparisons. The Ventana Fast is 40,800 millimeters scan per second. The Ventana Wide is 51,200. And we actually, in this paper we just published, we went up to 76,800 millimeters per second. And so we could actually do a 3.2 millimeter by 3.2 millimeter scanning with 24,000 lines per second, doing a 4x magnification of the scanning. This also works with adaptive optics, so you can increase the range of adaptive optics. This is Chae-Hong Yu, which is who's the engineer behind this work. So again, this is the Venn diagram that's similar to John's. Conventional microscopy optics are really limiting our our optical design space, and what we're trying to do is push beyond that for new applications. Thank you.